Welcome back to Mechanical Systems Design. In this video, we will launch Project 4, and it's a great project. It's our last project in the quarter, and it really brings together all of the technical skills we've been developing and introduces some new ones. So let's take a look at the project description. So I'll quickly go through the project description, but of course you should also separately read it carefully in detail. We're calling the project Incept, and in it, you will work with a team to design, fabricate, and test a robot that will climb up the edge of an open door, pulling behind it the heaviest load possible. And you're going to, of course, fabricate the robot using some materials we've given you and your 3D printers, perform some experiments characterizing its performance, upload videos and test data online via form, and submit a brief written report. The learning goals here are to apply this design approach we've been learning this quarter using these creative ideation methods, back-of-the-envelope analysis, computational methods, and tests of functional prototypes in an iterative process to a more complex problem in a team setting. That's one goal. Another is to learn how to effectively incorporate multiple custom and catalog components into an assembly. And that's something we'll be learning about in our readings and videos over the next week or so. And finally, to increase the level of sophistication in our use of models of motors and gears, our power analysis, and also our mass efficient component design, drawing on static analysis and stress analysis, buckling analysis, that sort of thing, using back of the envelope and finite element analysis methods. Now, before we get started, this is probably a good time to check that you have all the materials you need, including your functional Tamiya 72001 gear motor kit and your adjustable power supply, but also that you have the little shafts and bearings and longer wire leads that we provided to connect your motor to the power supply when you're moving a big distance. If you miss anything, please let us know so we can get it to you quickly. So what is the task here? Well, the theme of this project is inspired by the 2010 movie Inception. And in particular, this scene, we have Ariadne, who's a new architect of dream worlds, a sense for what it's like to relate to beings of these spaces. You can see the city is and at some point, characters don't have the magic of the world of Inception, but maybe we can make robots that drive up and down vertical surfaces. And so that's exactly what we're going to do in this project. And you can read the details here, but the big idea is that we're going to find a door that you can open somewhere in a space that you have access to, and design a robot that will travel up this vertical surface of the door. And your robot can touch the door anywhere on a vertical surface. It can't touch on any non-vertical surfaces of the door. It can touch on both sides and on the edge. It can be any size you like, as long as it is able to complete the task and doesn't make contact with anything other than the vertical surface of the door. It needs to lift itself and a payload together a height of 0.8 meters. And this needs to be a real door with a thickness of at least 3 centimeters, which is a standard size. A little bit bigger than that is a standard size for interior doors in North America. If you have special circumstances and you need to create a pseudo door, please get pre-clearance from the teaching team. And the payload should be as large as possible, while the robot can still lift itself and the payload that distance of 0.8 meters within 3 minutes. Much like in the last project, we will make the robot using provided components and your 3D printer. So you have to use the Mabuchi motor that we've given you. That's part of the Tamiya kit. And you can use the Tamiya gears as well if you like. That should be the only source of mechanical power in your system. And you can power it with your variable power supply. That should be the only source of electrical power. You can also use all of the shafts and bearings that we provided to you. Now, due to some restrictions on what we could ship to different places, we gave some of you ball bearings and some sleeve bearings, and we've got some of the key specifications here. If you received one and you'd like the other instead, please feel free to buy it, but you shouldn't use any other catalog parts than these. You can also fix broken PLA components or do some little tweaks or make connections with common household items like super glue, hot glue, popsicle sticks, tape, rubber bands, stuff like that. But this should not be the primary way in which you fabricate the robot. We've done some tests with the Tamiya gears of their strength, which could be handy, and you can read about that there. We've also given you a tool to make your own custom gears that you can 3D print, and there's a description of how to do that here. We've got some tips on how to go through the design process that are worth reading, and a little bit about your team. So we have assigned you teams with a diverse group of students to try to balance backgrounds, your schedules, and your requested teammates. And we have either 3 or 4 team members per team. One of the important things that you need to do in this first week, in addition to reading the project description carefully and starting to brainstorm ideas, is to hold a kickoff meeting. And at that meeting, you should discuss your team goals. Do you want to try to, lift the heaviest weight, or maybe just do the minimum thing to pass the project? Both are fine, but you'll have to come together as a team and decide on what your goal is. And this is going to require some compromise. And then once you've agreed upon a compromise goal for the team, stick with it through the project. You also want to set roles: who will lead this or that big project thrust. Set some meeting times. So you'll have a little bit of time in some of our coaching sessions to meet, but you also want to set up separate times. And I'd aim for 2 or 3 separate times per week to meet as a group and work on the project together. And of course, you'll need good asynchronous communication. And everybody is different. I don't know if you like Slack or text threads or an earpiece, but get everybody set up so that you can communicate well for the duration of the project. And of course, set a team name. Clever names appreciated. Now, while we're doing this project as a team, each individual member will have to fabricate their own fully functional robot and will conduct their own tests. And then we will use the average of the tests of all team members as the single one performance-based grade for all team members. So you are inextricably linked. You will rise together as a team or not rise as hard together as a team. So much like our other projects, we'll have a performance-based grade element, and you'll run tests and submit your data. And there are 2 main components of the performance-based grade. The nominal component is a little different in this project. You'll get 5 points for the full project for having a complete robot. You'll get 10 points for having a complete robot that hangs stably on the door with at least 1 kilogram of load. You'll get 15 points for a complete robot that climbs up the door for at least 10 centimeters with at least a 1 kilogram load. And you'll get 20 points for a robot that completes the full climb with at least a 1 kilogram payload. And if you get the full nominal, then you're eligible for an additional 10 points based on the magnitude of the payload that you lifted. And this is calculated really similarly as in prior projects. We'll give out some awards for the largest payload, manufacturing excellence, which will be for the best built robot, averaged across an entire team in both cases there, best style, and that you can take that in any direction you like, and the best summary report. The summary reports will be really similar. We'll add a new front page here that includes the team members and the name of your team. Images of the robot, you should be sure to include at least one image from everyone's hardware, and you can note them on there if you like. And then we'll have a summary page, 500 words, explaining what your design is and why it was a good choice for this task, and list your choice of applied voltage and motor to robot speed ratio. That's the radians per second of your motor to the meters per second of your robot, and your estimated and measured values of the motor current, the time to get to the top of the door, and maximum payload that your robot will be able to lift. And all of these are just used for us to understand your design process. You'll then have a transmission page in which you'll explain your process for choosing the applied voltage and motor to robot speed ratio. And you might want to use some equations, figures, a little code, whatever you think helps best make your case. And an analysis of the power flow. So where did each joule from the power supply end up? And this all significant power sinks should be included in your analysis that are separable. And then finally, we'll have the same number of component design pages as there are team members. So if you have 3 team members, you have 3 pages, and if you have 4 team members, you'll have 4 pages. And each one, you'll list the team member who led that page, an image of the custom component that you are describing, description and reasoning section, back of the envelope analysis, the critical back of the envelope analysis for this component, and a critical finite element analysis for this component. So that is what comprises your summary report. And then finally, you'll complete a self and peer evaluation in which you will describe your own contributions to the project and collaboration efforts in the project, and strengths and weaknesses in both things, and the same thing for your peers. And this is great because it helps your teammates to learn what they did really well and what areas they could improve. And the more specific and proactive your suggestions are, the better. And we'll give you a score for this component based both on the quality of your comments to your peers and on your peers' perception of your contributions and collegiality in the project. So the final project grade will be 30% based on objective performance, 60% on your report, and 10% on peer evaluations. This is a really challenging and exciting project. Have fun with it. You have the skills you need to make some really awesome robots.